So this is the beginning of chapter 19, which is called Spectrophotometry, Instruments and Applications. This is very much a continuation of chapter 18. Chapter 18 got us some background on light and Beer's law a little bit, talking about how that works. So chapter 19, what we're going to be focusing on is the instrument itself, that we make the absorbance or transmittance or percent transmittance measurements of. And so we'll be looking at the instrument and then looking deeper at what is happening with the molecule during this process of it absorbing light. So that's what we're going to be focusing on. So this video is about the spectrophotometer, but it's just part one. We're not going to go through all parts of the spectrophotometer in the same video to try to make things a little bit, shorter. So first, some background. So I showed this image back in chapter 18. It's just kind of a generic image of a spectrophotometer, an instrument that makes the measurements that we've been talking about that we use with Beer's law. Spectrophotometers, the ones we're focused on in chapter 19, use visible or ultraviolet light as their light source. Now, this type of image would be something that I would expect that a student in this class could draw. So if you were asked, say, to show the parts of a spectrophotometer and the order in which the light travels, that would be something that I would expect. And pretty much this picture gives us that. We are going to, before the end of this chapter, talk in much more detail about each of the boxes on the screen, except for the computer to display results. I don't care about that. We're going to talk about the different light sources, what a monochromator, which is the wavelength selector. We're going to talk about the cuvettes that the sample resides in. We're going to talk about the light detector at the end. So this is the generic pieces and order of a single beam spectrophotometer. So a beam, I mean like one beam of light coming from the light source. And so yes, I know here there's a bunch of squigglies. That's trying to show all the different colors of light coming out of the light source. But from the spectrophotometer, or from the monochromator on, there's just one stream of light that's being passed through the instrument. And so that's a single beam spectrophotometer. We will look at a double beam spectrophotometer here soon, and that will be important that you will know the differences between a single and double beam spectrophotometer and be able to draw this diagram for both of them. Okay, and so as it was mentioned in chapter 18, the purpose of a spectrophotometer is there's a linear relationship between the amount of light a molecule absorbs and its concentration. So we can see this if it's in the visible spectrum. The darker a color of a solution, the more concentrated it is. The lighter the color, the more dilute it is. And so the darker the color, the more light it absorbs. The lighter the color, the less light it absorbs. And there's a linear relationship between that actual concentration value and the amount of light that it absorbs. And when we're looking at the amount of light it absorbs, we're always going to be comparing it between the amount of light that we shine at the sample and then the amount of light that does not get absorbed by the sample. That's what those two things are. The subscript 0 means the initial amount of light leaving the instrument. And the P at the other side is looking at the amount of light left over. Sometimes these P's are I's for intensity instead, but this textbook uses these symbols, so that's what we're going to stick with. So again, this is kind of defining those values. The radiant power, the incident radiant power, which again is using the symbol of P, not the 0, is the amount of light that the instrument shines at our sample. Now, if we look back here, the detector, which detects the light, there's not one right here, which means if we need to compare P naught to P, how the heck do we know what P naught is? Because there's no detector right there. And there can't be a detector right there, because if there's a detector right there, then the light stops and it never goes through the sample. And so that doesn't work for us. So what we need is a way to measure both P naught and P. Well, to measure that P naught, what we need to do is make sure that the first sample we do, or a sample that we test periodically, and we put in the cuvette, which is the container that holds the sample. That's the container name, is a cuvette. That in that sample we put what is called a blank. That blank could either be a pure solvent, so just the thing that we use to dilute it, or more likely and more accurately, it's going to be a solution that contains everything that our regular standard solutions do, other than the analyte that we're testing. So the sample, the molecule that we're testing, will not be present in the blank, which means P naught, P0, and P should be the same because there's no light being absorbed by the sample. That's the only way for us to get P naught is to blank our instrument. So because again, the detector comes after the sample. We don't want it to just be straight up air because the light needs to pass through the cuvette, the container, and it needs to also be exposed to all of the other chemicals that are in our sample, except for the one molecule we're looking at. So that way, if any of the other molecules absorb light at that wavelength as well, we don't want that to inflate our concentration of our molecule because we only want to measure the molecule. So the only thing missing from the blank is the molecule that we are directly measuring. Okay, so when we do our spectrophotometers, I already mentioned this in chapter 18 when we looked at lambda max, we do one wavelength at a time. Okay, and we need to choose the wavelength that we set our instrument to as the lambda max, the wavelength that gives us the maximum absorbance for the analyte, for the molecule that we're testing. There are some exceptions to that. We don't want that wavelength to be super close to the low end or high end range of the instrument because we don't get as accurate readings as that. So like our ultraviolet instrument is usually doesn't get smaller wavelengths than 200 nanometers. So we don't really want to be like between 200 and 250 nanometers because that's where the light bulb, is not working as well. So our instruments are actually, they're not perfect, of course. So there's sometimes a plus or minus nanometer one, like a plus or minus 1 nanometer range to either side. Like we set the instrument to 510 nanometers. It's more likely to be 509 to 511. It's going to range maybe a little bit between there. So we want it to be kind of consistent right around that, but then drop off noticeably. So it's not measuring as well from there. So every compound has its own lambda max, has its own maximum wavelength. In order to determine that lambda max, we need to test it with the instrument first. Although that is something that you can look up. There are tables that give you the lambda max, but usually it's still a range. So you would want to test the sample that you're measuring on your instrument, ideally on the day that you're going to test it, at the temperature that you're going to be testing it, at pretty much the same time that you're going to test your sample. Now that being said, in industry, so like in companies, they don't repeat this. So if they're assuming that their instrument they're using the same instrument all the time, and they're assuming that the temperature of their lab room is going to be pretty consistent. And so they will determine the lambda max for their instrument at their operation and then use that same wavelength every time they do that test. They still have to find the extinction coefficient for Beer's law every time they do the test, but the lambda max it's different for every chemical, for every molecule, and it's technically should be determined with every instrument at every temperature, kind of pretty much every day. We want to make sure the conditions are consistent between what we choose to do and then when we actually do the experiment. But we can't say, oh, well, we always test them at 510. No, you might always test iron at 510 nanometers on this instrument in this lab room. That's fair. But if I wanted to test chromium, that's a different wavelength. Okay. When we're looking at absorbance values, it says the ideal absorbance for most instruments is between 0.3 and 2, where 2 is really the maximum absorbance that it really should be able to measure. The best wavelength values are kind of in the 0.4 to 0.8 range are the most, when the instrument is typically most accurate. So if we could keep the absorbance of our sample, our unknown, in the 0.4 to 0.8 range for absorbance, that would be the best. So when designing an experiment, like when I'm figuring out the procedures for your guys' lab, I had you do dilutions with your unknowns deliberately, oh my gosh, to try to, in a perfect world, get your absorbance of your unknown to be in the 0.4 to 0.8 range. That doesn't mean that it doesn't work any other, like it's not good at other wavelength or other absorbances. That's just the best. We don't want to go above 2, and we don't want to really go below 0.3 because it's getting too low, and above 2 is saying it's above 100% of light is being absorbed, and that's really not real. So these are just some parameters for us. So again, we've seen Beer's law. That was from chapter 18. We have to first make standard solutions where we know their molarity and measure their absorbance to make a graph where we have a linear relationship Beer's law only works if it's a linear relationship, where m is the slope, which is the extinction coefficient times the path length, not the b like the equation of the line, but b like the path length, how wide your cuvette is. So you would know the length of your cuvette, so you could solve for the extinction coefficient. So you always would make multiple standards, ideally like 5 standards, know their accurate molarity, measure their absorbance, make a graph, get the slope, and then you can measure your unknown, and then use the extinction coefficient determined from the slope to do the Beer's law calculation to solve for an unknown. So with spectrophotometry, we always, number one, have to make standards to make a calibration curve before we can test our unknown. Always. Where the slope is the extinction coefficient or the molar absorptivity. Those words mean the same thing. So part A of every experiment is standards, always, and then make a graph and then get the slope. Now, what's great is the instruments that are operated by a computer, doing the graph and figuring out the slope is part of the program, so you're not having to switch over to Excel to make your own graph. But it still has to be done. We just, the more money you spend on an instrument, the better the instrument's going to be. So here's looking at a double beam spectrophotometer. Okay, so we talked about a single beam, which looked like the part that I'm circling right now was what was in the single beam, pretty much, other than this thingy right there. So a double beam spectrophotometer is actually, so you've used both. You will use both by the end of this semester. The single beam spectrophotometer are the spectrophotometers that sit on the lab bench where every student kind of gets their own. There were new ones and there were old ones. There was just one cuvette that you used the whole time. That was a single beam spectrophotometer. The double beam spectrophotometer goes along with the caffeine lab. And in that one, there are 2 cuvettes. And so the point of a double beam spectrophotometer is to pretty much measure P0, P0, that amount of light being tested our sample, every time we test a sample. So it's not like when we blanket, we can figure out P0. And so it's constantly being compared to that. So it's going to be more accurate. So what happens is the parts of the instrument are all still there. Light bulb, check. Monochrometer, which is the thing that filters out every wavelength, but the wavelength you use, check. Cuvette, where our sample goes, check. Detector, check. And then the computer display, which we care less about this. Like, we know it exists, but we're not going to talk through like the programming on how it goes from there to there. The thing that's different is the light that comes out of the monochrometer, the light that comes out of the filter, is split into 2 different paths. One path is following the arrow that I just drew, and the second path is going to follow the purple arrow that I'm drawing. So what happens is there's a mirror that takes the light coming out of the monochrometer and splits it, so half of it goes straight and half of it curves down, and then there are 2 cuvettes. The sample cuvette, which is right here, and the reference cuvette, which is right here. The reference cuvette contains the blank solution constantly. The sample cuvette you change out. So you will, add your blank first, and then you will add standard 1, and then you will add standard 2, and then you will add standard 3. The reference cuvette has the blank the whole time and you don't take it out. But what it's doing is giving us that P0 value to compare against the P value, which, remember, transmittance is just that as a ratio. Percent transmittance is that as a ratio times 100. That's a 100. And absorbance is the log of the inverse of that. Whatever, those are the values that the instrument would give you. But it's more accurate because we always are comparing it from P0 to P, which is like the definition of what these units are. The transmittance, percent transmittance, and absorbance have to compare those 2 numbers. So that's the amazing part of them, is it's gonna be more accurate. It takes care of, like, if there's some sort of weird fluctuation in the electric current, so like when it's plugged into the wall and there's kind of a surge of electricity, that would impact the amount of light that was coming out of the instrument, which would impact like the P value. So if we're using a single beam spectrophotometer, with that P value just jumps for just a second because of the electrical current, which we can't control, we would see error then with our results. Well, using a double beam, we don't, because if both of them would jump at the same time, and we're looking at the ratio between them so it would stay nice and consistent. So they're more accurate. They're just better all around. The bad part about them is they're way more expensive. There's more parts. Okay, there's mirrors, which is not terribly expensive, but then there's the motors that run the mirrors to make sure um, that they're angled correctly. And some with these double beam spectrophotometers, you can hear the little motors working when you use them. So double beam spectrophotometers are better than single beam spectrophotometers, but the thing that offsets it is cost. We have 8 single beam spectrophotometers that we just set out on the counters and let students use. We have 1 double beam spectrophotometer where the only students that are allowed to use that are those in quantitative analysis. Only instructors are allowed to use that instrument otherwise. So you guys should feel special about that. As you should anyway, because quantitative analysis is clearly the best. But I would be prepared for like a test to talk to me about the differences between double and single beam spectrophotometer, including being able to draw a picture showing the differences. So showing that picture versus, I have to go back too far, aren't I? That picture. I could ask you to draw one or both, but I also could ask you to talk to me about the differences between double and single beam spectrophotometers in terms of pros and cons. So, looking at this is kind of going through what we've, already talked about, where we need to blank the solution, and the blank needs to be identical to our solutions with everything except for the analyte being tested, which means the molecule that we're actually testing. So, last thing in this video is we're going to start talking through the different components of the spectrophotometer. And so in this video, we're going to talk through the light sources. So then we'll move on in the next couple of videos to all the other parts. There are lots of different types of light sources, which I'm going to call typically lamps, available depending on the instrument and the point of the purpose of the instrument. So a tungsten lamp is great in that it does all of the ultraviolet, like it does the entire wavelength of the visible and part of the infrared and part of the UV. So this right here is the different wavelength ranges that lamp would operate under. A concern is it has to be at 3000 Kelvin. They figured out how to make that work to where it's, doesn't feel super duper hot to things. So a tungsten lamp would be one that might be part of a ultraviolet spectrophotometer, because a UV spectrophotometer would measure both ultraviolet range light and visible range light. So a tungsten lamp could be part of it. But the issue is the the ultraviolet goes down to 200 nanometers, and this one stops at 320. So we would need another lamp as well. So if we're doing that, a deuterium arc lamp, which usually is just called a deuterium lamp, would also be part of the instrument. So the instrument would have 2 light bulbs. A deuterium lamp, which goes from 110 nanometers to 400 nanometers, and then a tungsten lamp, which goes from 320 nanometers to 2500 nanometers. And what would happen is, depending on the wavelength that you selected for the instrument to run, it would turn on one of these lamps, or it might turn on one of them and then switch to the other, depending on what's going on. The graph down here is just showing you how these lamps work in tandem. So like the deuterium lamp is the only one that goes from 200 up to 320. It's the only one that goes from 200 nanometers to 320. The reason why I'm not going below 200, because that's getting outside of the UV range, and we're not going to worry about that. And so obviously the deuterium lamp, the higher the curve, that means the stronger the light intensity. So it's really good, like kind of from like here to, like there, and then it's kind of going down. And then the tungsten lamp would turn on if we were looking at a wavelength, above that. So kind of in this range, the instrument, knows when it wants the deuterium lamp and when it wants the tungsten lamp at this. So typically at 360 nanometers is when the deuterium lamp would shut off and the tungsten lamp would start. So I could ask questions about what are some common light sources of UV visible spectrophotometers, so instruments that go in both the UV and the visible range. These two would be one answer. A tungsten lamp and a deuterium lamp together would be one possible set of light sources, where knowing that the deuterium would work sometimes and the tungsten lamp would work at other times. The instrument that we had before the one we have right now This is exactly the setup. And so there were two little buttons that I could have manually turned, the tungsten lamp on or the deuterium lamp on, but I typically let the computer, like I just set the wavelength and it decided which one was best. The deuterium lamps, what they do is deuterium, which is hydrogen 2. So it's got H2, but where both atoms are their isotope, where they each have hydrogen has an extra neutron. Deuterium is part of this lamp and it deteriorates just naturally and it emits this light as it does that. The unfortunate part means whether or not you turn on your deuterium lamp, you need to replace that sucker every for us it was every year, but it depends, every couple years, because it just will naturally wear itself out because it's basically on all the time. They just block it off to where its light is not reaching the sample if we're not turning on the deuterium lamp. So, these are not coming in the order that I wanted them to. Xenon flash lamps are the new one. That's what our new instrument has. So that would be an answer number 2 for different types of light sources for UV visible spectrophotometers. They're great because they are one lamp made out of xenon and do the entire range. So that means we don't have to, have multiple lamps because that's, the more lamps you have, the more fear that something's going to go wrong because if one of them is broken, then the instrument only works sometimes. And then what's also great about them is unlike deuterium, these xenon flash lamps last for at least 5 years at a time. So that's what our new instrument has, and we're excited about it. It's been working pretty well so far. And it was a little bit less expensive actually to do the xenon flash lamp than doing both the tungsten and the deuterium. So those are the two most common. Like if I asked, what are the two types of light sources for a UV visible spectrophotometer, I would want you to give me tungsten and deuterium is answer 1, xenon flash lamp is answer 2. These are just some other options for UV vis. The LED lights, those work. Lasers can work. Both of those are very narrow, though. They wouldn't have the entire range. But this is another answer to know. This is the light source if we're wanting the infrared range. It's the silicon carbide glow bar. And in organic chemistry, you will use an infrared spectrophotometer. So that's something I want you to know, that this is the light source for IR, infrared. That's its range. It's in wave number instead of in wavelength, because for IR, for whatever reason, silly organic chemists, they use wave numbers instead of wavelength. And if you've forgotten what a wave number was, go back, check out the first video in chapter 18. It's 1 divided by the wavelength is what it is. So these are the light sources. I would be aware of those 3 scenarios. Okay, the tungsten and deuterium together works for UV vis. Xenon by itself works for UV vis, and silicon carbide glow bar works for IR.